So what I want to focus on here is some of the big ideas from earlier in the course. And one of the things that we encountered first was something about voluntary response. The problem with voluntary response is that you're not getting a good representative sample. People are self-selecting to be inside of your data set or not, and that means your data set's probably not going to be representative of the population you're trying to target. And if that's the case, then there's a problem. You're going to have difficulty generalizing in that case. Now, the reason we want a good representative sample is so that we can get information about a population parameter. We'll talk about that in just a minute. For now, let's move on down to statistical significance and practical significance. I'd like you to know what each one of these means. You could have situations in which something is statistically significant but not practically significant. Or maybe it's both. Kind of depends on the circumstances. Although I'm struggling to think of a case where statistically significant, where something's not statistically significant but it is practically significant. If it's not statistically significant, I'm not sure you're going to worry about practical significance. In any case, statistically significant means you're rejecting H0, whatever test you're doing, that, yeah, it's beyond what we would expect just by random chance. So the results can be ascribed to, you know, some change in your data or one population versus another. Practically significance means the result is worthwhile. And the example that I always like to use is one from the author talking about the Atkins diet. After a year of being on the Atkins diet, people lost 3 pounds. And that was a statistically significant result, meaning if you did a hypothesis test that the mean weight loss was 0, that yes, you'd reject H0. They lost something different than 0. In this case, it was 3 pounds. So that'd be statistically significant. But is it practically significant to spend a year to lose 3 pounds and spending potentially hundreds or more of dollars? No. So you can be one and not the other. You can be both. There was one where you compared therapy versus surgery in terms of treating carpal tunnel syndrome, and I think the surgery, even though it was more expensive, had a statistically significant difference over the therapy, and it's practically significant because there was a much higher cure rate, like 20% higher cure rate, so had both of them. Let's move on down. Remind ourselves of some of the other basic things here. Some of the basic things that we covered would include frequency tables. So a couple things about frequency tables. You had your lower class limits. That's these numbers down here. So let me highlight those in orange. Those would be your lower class limits. Your upper class limits, of course, are just the opposite side of that chart, right over here. So those would be upper class limits. How about the class width? What's your class width in this case, in any of these cases? It's 5. Good. And I'm glad to see that somebody said 5 instead of 4. It's easy to go, oh, 24 minus 20, that's a difference of 4. But really you have to subtract adjacent upper class or adjacent lower class limits. So 35 minus 30 or 34 minus 29, you get a class width of 5. The class midpoints, well, for those, you're just going to average these and find out what's in the middle of those. So in this case, it'd be 22. And then, well, we got another one here that's 17, etc. And this is going to increase by the class width. 27, 32, 37, 42, and 47. Yay. So there's your class midpoint. That also goes by the name of class mark. So that's another term that you might see used for that. But let's move on to some more stuff from earlier on in the semester. As a society, we're really good at collecting lots of data. And when you just look at the raw data, it becomes kind of a challenge. It's like, well, what's going on? What is it saying? So we had a lot of measures of center. Measures of center would talk about what's typical in a data set. And there was a couple of them. You could look at the average, the arithmetic average. Arithmetic average also goes by another name. Does anyone remember what it is? The mean. You're not going to hear average used in this course very often. But the mean. How about the mode? What is the mode telling you about a data set? Yeah, well done. What data point is repeated most frequently? So there's your mode. And of the things that I covered here, there's one more that I'd like you to know, and that's the median. What's the median? It's the center. Dead center. I guess it depends on your distribution. So the median is the 50th percentile. Yeah. So the second quartile. Yeah, there you go. So the 50th percentile, that'd be P sub 50 equals the median equals the second quartile, Q2. Well done. So these are the three that I want you to know. You should understand the advantages and disadvantages of each of these. The mean, for instance, is sensitive to outliers. The median, well, that doesn't use all your data, so you're ignoring a lot. Now, in collecting data, what we're trying to do is trying to find out some stuff about a population, and that leads me down to this discussion. Population versus sample, parameter versus statistic. What's the difference between a parameter and a statistic? What is a parameter? What is a statistic? What's a parameter?
Numerical value of a population?
Numerical summary of a population, yes. Numerical summary of a population. So, numerical summary of a population. Let me put of a characteristic. Of a population. And the same thing is going to be true with statistic, except what difference? Yeah. So this is a numerical summary of a sample. Numerical summary of a characteristic of sample data. Nice. Nice. Now, let's kind of scratch our brains on this again. The difference in notation for these things. I'll give you a minute to write it down for yourselves. If you're watching this video later, then maybe you want to pause it for a second. Try and write in these values before I write them down for you. Wish that was the exam. All right. Joy, let me start with you, please. What's our notation for the sample mean? Bridget, some help? bar. And then the population mean? Mu. All right. Ian, how about standard deviation? What do I use for sample and population standard deviation? S. The Greek letter. Sigma. Well done. Well done. Ni? How about population proportion? P hat. And P. Good. Correlation. Savannah? R. Rho. Yeah, well done. And the last one, Nicole? Linear regression? Can I phone a friend? Ashley, some help?
Y hat equals, is it B0x plus B1, or is it B1x?
B1x plus B sub 0. Yeah, there you go. And for your linear regression in terms of the population, I'm just going to scoot it down a little bit. Y equals beta 1x plus beta 0. Yeah, well done. So a nice dose of your Greek letters here, except for your population proportion. But the reason that we sample is because it's a lot of times it's difficult, if not impossible, to get these values. We want to know these values quite often, but we can't collect data from an entire population. So if we can't do that, the best we do is do a sample and then use our sample to try and make estimates here. A lot of times you surround these estimates with a little wiggle room for error. What's that wiggle room called? What are you doing? Yeah, it's your confidence interval. So you can be 95% confident that this value is between, something plus or minus an error term, etc. So we're trying to figure out what these are, and that's what's going to be the goal of our hypothesis testing. Now, before you get to hypothesis testing, there's a few things we got to understand. And that all starts with probability. So I'll admit it, the Lions used to be my whipping boy for probability of 0 in terms of getting to the Super Bowl, but I think that's changed a little bit this year. In fact, maybe we'll do a little problem about that. Something that's certain, well, that has a probability of 1, and then you have everything in between. But one thing's for sure is that probabilities are between 0 and 1. So if you want to get a problem very wrong and not get any partial credit, give me a probability that's outside of there. All right? It just can't happen. So keeping that in mind, let's look at these. So cross off in your mind or copy them down and cross it off in your paper, which of these are actually valid probabilities. So let's take a look at those. All right, so let's kind of go around the room. Which of these should I cross off? Ryan, give me the first one I should cross off.
5/3.
All right, let's cross off the 5/3. Thank you. Nicholas, what's the next one I should cross off?
-2.5.
-2.5. Good deal. Izzy, let's keep it going. What else should I cross off? Just give me the next one.
Me?
Lizzie.
Oh, you're fine, 250%.
Thank you. Q? What else could I cross off? Yeah, 7-3. That's a ratio. Now you can turn those ratios into probabilities, but as it's written, it's not a probability. Cool. How about the next one? Nicole?
The ratio 5:1.
All right. 5-1. Now, this one, I kind of, in my heart, I want to cross it off. It doesn't feel right. Although, I could tell if I did mark somebody wrong like this, they would come up and complain because they're like 50 minus 50 is 0. and 0 is legitimate probability. So even though I think this is supposed to mean a 50-50 probability, I don't like it. I won't use that example on an exam, but yeah, that one probably does qualify in here. How about the last two? Anything I can cross off there? Yeah, 2.017. Probabilities are between 0 and 1, and that's it. So, each week, the guy that organizes our Thursday morning hockey puts the teams together, and he always puts me on his team. What's the probability that I'll be on his team? 1. Yeah, something that always happens is 1. He actually had to change it up because he was getting complaints. All right, let's keep going. Now, one of the things I've done is I've kind of backed away from probability a little bit on the final exam. Mostly I'm trying to think of the kinds of things that you're going to need moving forward and then things that are going to be helpful outside of this class. One thing that's helpful to know is what the average of a probability distribution is. So we use mu, but it also goes by the term expected value. That's what you would expect if you perform some kind of experiment again and again and again. Now, if that expected value regards your probability of winning a game of chance, you want that expected value to be as big as possible. All right? Chances are it's going to be negative. Why negative? If you're playing a game of chance, especially at a casino. Yeah, so the house can win, right? The odds are stacked against you. If there was a positive expected value, the casinos wouldn't be able to keep their lights on. They'd be going bankrupt. So we'll talk a little bit more about that in just a minute. But let's talk about odds for and odds against. An instructor plays a game called Words with Friends, and there's one person I play that, I don't know, doesn't get the message that, all right, find somebody else. But let's take a look at this and see if we can't come up with some odds for winning. This is odds from my perspective. So the odds for me winning would be 20 to 5. 20 times I win, 5 times I lose. Okay. What about the odds against me winning? What would those be? 5 to 20. Yeah, 5 to 20. Just turn it around. Now, how about the probability of me winning? So now we got to go from odds to probability. What's the probability that I win? Do I divide the two? In what way? What should I write?
5 divided by 20.
Well, I want to start with the 20 in the numerator. That's the number of ways I can win. But in the denominator, what do I need?
Total.
The total. 20 plus 5. So you need both of those together. So chance of me winning is really going to boil down to 20 over 25. That's the chance of me winning. Let's put that in perspective with respect to the Lions. And I'm not sure about you guys. Do you guys hear ads or see ads for FanDuel and all these stuff all over the place? DraftKings. Yeah, I get tired of it. So, but in reference to that kind of thing, if you looked up the Lions this morning on the odds to win the Super Bowl, you'd see that they're a plus 260. That means if you bet $100, you win $260. So that's your payout. So that's your net winnings. So really, you give them $100, they'd give you back $360. What's that as in terms of a probability of winning? Turn that into a probability. Well, in the numerator, what are you going to put? You're going to put the number of ways that they can win. And probability of winning, this is saying that there's 100 ways that they can win. That's in the numerator. In the denominator, what am I going to put?
The total.
the total. 100 plus 260. So 100 over 360 is about 0.278. So about a 28% chance of winning. It's not too bad, considering that there's a lot of teams in the league. Yeah, it's not too bad. That's certainly a lot better than the near zero that I used to give them every year. Yeah, please.
So, even though it says the odds are plus 260, how come we're putting 100 in the numerator?
How come what?
How come we're using essentially the odds for winning as just the number we're betting?
Because to me, what this says is it's a payout ratio. So it's giving you the net profit versus your amount bet. You bet 100, you win 260. So it's telling me that there's 100 ways they can win and 260 ways they can lose. So the total of those is your denominator, which is the 360 things that can happen. Appreciate the question. Let's remind ourselves of, yeah.
I'm so sorry. Really quick for the answer, we have that decimal. Will you expect us to do that, or will you?
Oh, I just did that just so that, because I don't think many of us can look at, 100 divided by 360 and say, okay, is that good or bad? So I just put the decimal there out of courtesy.
Okay.
Yeah.
But just
If I want a decimal and if I want specific number of decimals, I'll say, give me a decimal. Generally speaking, I'm happier with fractions because sometimes your answers can be really close. You could have the wrong answer, and the decimal values would hide that. So I'm generally happier with fractions. Good question. Let's go back to mu and sigma. One of the things that we had early on was the range rule of thumb. Oh yeah, going way back on that one. And a specific, this is what helps you decide what's unusual and what's not unusual, what's significantly low and what's significantly high. So significantly low values, those start at 2 standard deviations below the mean. Then you have significantly high values, which start at 2 standard deviations above the mean. And stuff in between is just not significant. So, okay, we'll keep those in mind as well.
Quick question.
Yes,
What question are we on?
it's just a handout that I put on D2L.
Okay. All right, fantastic. Thank you.
Based on data, sample data, newborn males have weights with a mean of 3295.5 grams and a standard deviation of 608.9. Newborn females have weights with a mean of 3008.8 grams and a standard deviation of 5.7 or 575.6 grams. Who has the weight that is more extreme relative to the group from which they came? A male who weighs 1,700 grams or a female who weighs 1,700 grams? And actually, they'd be close. But what are we going to use to decide this? What's going to help us figure out, well, which one's more extreme? What could we use to measure that? Boy.
3295 minus 17 divided by the standard deviation.
Oh, and what's that thing called?
Some word, I don't know.
It's not a word, it's a letter. Z. It's your Z-score. Yeah, so well done. So you're going to calculate your Z-score. That's going to be I'll give you 2 different notations for it. There's x minus mu divided by sigma, or x minus x bar divided by s. So depending if you have sample data or population data, one of those two, you're going to get the mean minus the standard deviation, or excuse me, your data minus the mean divided by the standard deviation. So let's take a look at those calculations for each of these. So in both cases, I'm going to take 1700 as 1700 as the weight of the individual, so that's our data point. And in one case, I'm going to take and subtract 3295.5 divided by 608.95, or 608.9. So 3295.5 divided by 608.9, 3008.8 divided by 575.6. Now when you take out your calculator to find these numbers, I'd suggest that you use parentheses. I mean, there's fancier ways you can do this. When you do that, just do parentheses around the numerator, 1700 minus 3295.5, parentheses divided by 608.9. It's about negative 2.26 or negative 2.62. And if you do likewise over here, I think you get about negative 2.56. So which one's more extreme? Which one's more extreme?
The males.
Males. Yeah, they're farther away from zero. They're farther away from the mean of their data set, if you're counting how many standard deviations away you are from the mean, which is exactly what z-scores do. Okay. Sticking over here, when are two events independent? Yeah, the outcome of one doesn't affect the likelihood of the other one. Nice. What about mutually exclusive events? Sometimes I think the author might refer to these as disjoint. Yeah, Jackson.
It's like if there's a yes or no answer to the event, so like you pass or fail a test.
Okay, so yes or no. Let me add to that a little bit. So if one happens, the other one can't. All right, you either voted or you didn't vote. You're either pregnant or you're not pregnant. You got heads or you got tails. We're not counting sides, although there's a statistically small chance that you can get a side with the right coin. But in any case, mutually exclusive events can't happen at the same time. They just can't. If one happens, the other one can't. So, let's see. I'll just write down if event A happens, event B cannot happen. All right, there we go. Let's move back a little bit towards probability. And these are actually some counting rules. It's one of the fun things that I enjoy about statistics is our counting rules here. And this symbol here, the factorial, I enjoy introducing that one. Factorial, 4 factorial represents the number of ways that you can arrange a group of so many objects. So like 4 factorial is how many ways I can arrange 4 objects, 5 factorial, and so on. It is a true thing that I can show you if you take me for Calc 2, that 0 factorial does equal 1. You can try it on your calculator if you'd like. But let's take a look at some other things involving factorials and such. Let's see, that. Now, one of the big things that it led to when we were talking about factorials was permutations and combinations. What's the big difference between these two? Yeah, if order matters or order doesn't matter. Which one does order matter? Permutations. So order counts. So when you're dealing with permutations, order matters. Combinations, order does not matter. All right, so where does order matter? Well, let's take a look at a couple examples, see where order matters and where order doesn't matter. So let's look back at our exam, the one that you took just the other day. And I gave you something like this, asking you to figure out, well, what value of R, the linear correlation coefficient, goes with each of these plots. So you had 5 of these slots and 8 values that you could plug in here. So the question was, how many ways could you fill out this problem? How many ways could you answer it? So I asked you to calculate this number, or at least show me the notation. The question for you is, does order matter?
No.
You got to vote for no. Ian, is that you're agreeing with her, or are you saying the order does matter?
I think it does.
You think it does? So let's take a look at this. Suppose I just said, all right, this one would be a 1, this one would be a -1, a 0.99, a 0.5, and a negative 0.95. Would that be the same as putting a negative 0.95 here, a 1 here, a -1 here? Would those be different answers? Yes. And one of them could be right and one of them could be wrong. So the order definitely matters there. So in that case, what would we do? Would we do permutations or combinations? Permutations. So why don't you take out your favorite tech, whatever you're going to use, and try calculating 8p5. Now, in case you're struggling to remember, here's one of the things that I'll give you on your final exam, and that is a sheet with all your commands. This will be actually printed on your exam, and wait for it, here we go. And I'll even put a guide to your StatDisk, some of your StatDisk commands. Yeah, I know. Whoa, yay. All right, so in any case, you should be able to get, I think, about 6720. There you go. 6720. So order matters. How many of you grew up with Webkins? You're familiar with Webkins? Like, oh yeah, Webkins. No matter how much I told Grandma, no, she doesn't need another Webkin. My daughter always got Webkins for Christmas and birthdays. She had like a bunch of them. So if she had 18 of them and she was going to put 12 of them up on her bed, are we talking combinations or permutations? How many groups of 12 could she put up on her bed? Combinations. So yeah, it'd be 18 choose 12. So 18 choose 12. All those things drove me crazy. One of the games you can play online or on your phone is Connections. And it's kind of cool. What they do is they'll give you 16 words and you got to figure out, well, what's the connection between those words? And they're in groups of 4. Now, if I look at the remaining remaining 12 words here, how many groups of 4 can I choose? Would that be permutations, combinations, factorial? Which one am I going to use? I need to choose the correct group of 4. Like the first group of 4 that I got correct was hat trick, three-peat, trifecta, and triple crown. They're all trios of sports achievement. But what's the next group of 4? How many groups of 4 could I choose? If I just had no clue, how many groups of 4 could I choose? What would it be? Is that a permutation or a combination?
Is it a permutation?
Is it a permutation? Does order matter? Does it matter if I choose, for instance, tape, roller, what else? Paint, and drop cloth. Those are all things you would need to paint. Does it matter what order I choose them, or is it just good enough that I chose the right 4? That I chose the right 4. So is that a permutation or a combination? Combination. Good. So how many combinations are there? 12, choose 4. You should be able to verify for yourself that there's 495. All right, now for the bonus round. What's the next group of 4? Ooh.
I can't see the words that
All right, so let me zoom in then. Soapbox, home run, wings, Kentucky, sprouts, broil, demolition, and cheesesteak. So, pause the video if you don't want the answers. Give yourself time. Spoiler alert. All right. Soapbox, home run, Kentucky, and demolition. What are they all? They're all derbies. Soapbox derby, home run derby, Kentucky derby, and demolition derby. So they're all derbies. And I have no idea what these last 4 have in common. That's whatever. But you get that one by default. All right, so a little fun there. Now, follow-up question here. When you're looking at these 12 words there, there's 3 groups of 4 words that are the correct group. If you just blindly guessed and chose 4 words, what's your probability of getting your guess correct? What's the probability that you'll get a correct group if there's 3 correct answers here?
1 over 495.
Yeah, I'm guessing. I like that. Somebody said it back there.
1 over 3?
No, somebody else. Somebody.
The 3 out of 495.
3 out of 495. There's 3 correct groups out of 495 possible groups of 4 that you could guess, so you got a 3 in 495 chance of getting it correct. So, not all that high odds. Awesome. Let's keep going. So you might want to open up a Google Sheets doc if you don't have one open. And so one of the things you can expect from me would be, what should we call it? A list of all these commands. And rats, I'm missing something here. So in terms of binomial probabilities, one of the things you can look at is something called fits. What does fits remind us of? Fixed number of trials. Nice. Independent. Oh, well done. 2 possible outcomes. Oh, well done. Same probability of success throughout your trials. So that's when to apply a binomial random variable. And let's take a look at this problem. Why don't you read through it, try and convince yourself that you've got something that actually satisfies a binomial probability. So we have a fixed number of trials. How many in our trial? 8. We want to look at the probability of getting exactly 3 successes out of 8 trials, and at most 3 successes out of 8 trials. So both of those are probabilities that we can calculate with binom dist. So let's open that up. And I'm actually going to go through it a couple different ways. Let's see, that's over here. And okay, so let me ditch this real quick. So I'm going to start out with this one right here. Binom distribution with false. If I want exactly X number of successes, that's the one I'm going to use. Is binom distribution for false. So, okay. Let's do that. Now, a couple things we're going to need to know. We're going to need to know how many successes we want. That'll be 3. What's n for us in this case? 8 for our case. What's the probability of success for us? 63%. And then we're going to use false. So I'm going to type that in over here, give myself a little bit of room because I'm going to do some more fun stuff in a minute. So equals, all your commands start out with equals, binom distribution. Once you see that it recognizes your command, hit the tab. We want 3, 8, 0.63, false. And you should get about 9.7%. Yay. Now the next one asks you to get the probability that at most 3 will satisfy, or at most 3 people use their cell phones during meetings or class. So I'm going to do this a couple different ways. The first way is this. If you notice, I wrote down all the possible outcomes from this experiment. You could have 0, 1, 2, 3, or all the way up to 8 different people who would use their cell phone in class or meetings. And let's just take a look at this probability right here. Equals binom distribution. And instead of typing in the number 1, or excuse me, the number 0, I'm just going to click this space over here. So it gives me A1, comma, 8. There's 8 trials for all these, comma, 0.63, comma, false. Now that's going to give me the probability that nobody is using their phone, which is probably going to be remarkably small. All right. Now, what's the trick that I'm going to pull next? Do you have any ideas?
Drag it down.
Yeah, drag it down. That way it does it for all of my distribution. And in fact, if you notice at the bottom, I've got this number 1 here. What's that number 1? The sum. If you look at the sum of your data, and that's the formula I have in here, as I sum up all these values, I get 1. Your probability distributions always have to add to 1. Now there's 2 ways I can get this second part of the probability. One is to add up all 3 of those probabilities and get the sum. So I can just do that. Equals sum of these 3 values, click and drag, and that's what we want. There should be about 13 something percent. 13.07%. If you're fine with that, great. If you wanted to get fancy, you could copy that. And let's go over here and change the false to a true, because now it's going to give me the probability of 3 or less. And that's the same thing. So one way or another, you can get that probability. It's up to you what you feel most comfortable with. I think when I originally taught this, I didn't really do too much with the true part of it, but it's there if you want to use it. It's not a big deal either way. We looking okay with binomial probabilities there? Chapter 5? All right. Just as a reminder, the mean of a probability distribution is n times p. The standard deviation is the square root of n times p times q. What's q equal? Yeah, Q equals 1 minus P. So you can use this in combination with, for instance, the what is it? A range rule of thumb to decide what's typical and what's not typical. So I don't think I want to jump into that now, but that'd be a nice exercise to do on Google Sheets. Let's move down to chapter 6, where we start talking about this curve. What kind of curve is that? Yeah, it's your standard normal curve. So, very nice. We're going to work with a particular standard normal curve that has a mean of 64 and a standard deviation of 2.2. That's for the heights of women. And a branch of the military wants to require that heights of women would be between 59 and 77 inches tall. So, all right, is that more on the inclusive side or not? Well, good question. Let's find out. So, I think I'm going to draw myself a couple distributions, and I'll start with this one right here. If I ask you on an exam to label this distribution, what I'm looking for is for you to draw down a line down the center and put a number on that line. So if this distribution, X is distributed normally, the mean is 64 and a standard deviation of 2.2, what number should I put down here? 64. Nice. Now we're trying to find the percentage of the area that's between 59 and 77. So that's going to look something like this. Trying to find the area here to here. That's good enough. 59, 77. What command am I going to use to help me find that? Now let me give you a couple of choices here. Let's go back up here. I'm thinking it's going to be one of these two, but which one? Am I going to use norm distribution or norm inverse? Norm distribution. Now let me remind you that the important thing about norm distribution is it gives you the area in the left tail, the left of our value of X. So when I look at this one, I realize I'm going to have to do a couple different things. So the first thing I want to do is I want to find the area to the left of 77. But do I want all of that area to the left of 77? I need to get rid of this area, right? The area to the left of 59. So the command to do that would equal norm distribution of, let's see, let's start with 77, and then you want the mean and standard deviation, so 64 and 2.2, comma true. In this course, you're always going to be using true with norm distribution. And I'm going to do this all in one line, minus norm distribution. I got to subtract off something else here. Q, can you help me fill in what's going to come next? What's the second part of this going to be? To subtract off the area to the left of 59. 59. 64. Standard deviation 2.2, and then always with true for norm distribution. And that should be kind of a fairly high percentage. Should be like 98% or something like that. 99? All right. Thank you. So let me... Yeah. So here you go. About 0.99%, or about 0.988 if you want to round it to 3 decimal places. So are a lot of women getting excluded with this criteria? These are the ones that are included. So are you excluding a lot? No, no. Less than 1.5%. So nice, nice. Now there's a part B here as well. Are we okay with part A? Let's take a look at part B. Let's see. I want to keep my sheets in order here. So for part B, it says if this branch of the military changes the height requirements so that all women are eligible except the shortest 2% and the tallest 1%, what are the new height requirements? Okay, let's look at that. That's going to require a little bit of different work on our part. So let's talk about the shortest 2%. So X in this case is distributed normally with a mean of 64 and a standard deviation of 2.2. We'll start out with the shortest 2%. Where should that be? Where's that value going to be?
On the left.
Yeah, it's going to be on the left. So 64, and somewhere in the left tail, we're going to find the value that puts 2% of the area in the left tail. Okay, great. So how are we going to figure that out? Well, that's going to require, is that going to require a norm distribution command? No, that's going to require a norm inverse command. Norm inverse command doesn't have this true or false thing that you have to worry about. It's just your value, which is whatever percentile you're working with, the mean and standard deviation. So in our case, we want 2% of the area, which as a decimal is 0.02. So it's going to be equals norm inverse of 0.02, mean is 64, and standard deviation of 2.2. Let's see about getting that value. And pay attention about how we solve this one, because you're going to be up next for the next one. So, let's see. Equals norm inverse. What are you getting? What values are you getting?
59.481.
Thank you. 59.481. Now, if it matters to me exactly how many decimal values you give me, then I'll probably specify it for you in the problem. Otherwise, just give me a reasonable amount. That's fine. I can't complain if I don't specify it. Let's try the other part here. We want to exclude the tallest 1% of women. And there was actually a student in my morning class who would have been excluded by this criteria. So good for her. Let's see. Just like before, got a mean of 64. Where should I draw the tallest 1%? In the right tail. Good. So let's put that in the right tail. Try look it up. Try look it up on your Google Sheets. Try and find that value for 1% of the area in the right tail. So it's going to be another norm inverse command, but you're going to have to think a little bit. And if you get a value that doesn't make sense, then go back and figure out what went wrong. pause button go? If you get a value that doesn't make sense, so you can't fix it. Yeah. Really? Really? Yeah. Oh. Is it? All right. Are you guys getting values that don't make sense? Did you get a value that didn't make sense? So let's take a look here. Because this can happen really easily. Let me just copy this and naively say, oh, well, I want 1% here. But wait a minute. That looks bad, right? Because that's way to the left. Oops. That's way to the left of this. I expect something in the right tail. So what did I do wrong? Or what do I need to change up so that I get this area with 1% of the area in the right tail? If 1% is in the right tail, then what percentage of the area is in the left tail? 99%. So the key here is that I've got to type in 0.99 because that's how Google Sheet works, is it's giving you the area in the left tail. But when you draw these distributions, and a lot of times I'll put these distributions on your exam so that you can draw things and make sense of them. If you try putting in 58 point something, you realize, well, wait a minute, that doesn't look right. And hopefully you go back and change things. So the correct command should be norm inverse of 0.99, 64, and 2.2. What'd you get on that one? What's that value? 69 point what? 69.1, we'll call it 12. And that would be in units of inches. Well done. Well done. All right. Looking good on that one. We're going to stick with the normal distribution for just a minute. And this is going to relate to a problem that you should absolutely expect. This was the central limit theorem for us. Let me remind you of our handout back from the central limit theorem. That's not it. Where is it? Nope. Well, this is our work on the central limit theorem, but that's not it either. Where did that thing go? I know. I'll do it this way. There we go. Let's just copy this over and make it a little bit bigger. So the idea behind the central limit theorem is that it doesn't matter what you start out with in terms of a sample. You could be sampling from a normal population, which is this one here, a population which is skewed to the right, or a population that has a uniform distribution, or whatever population. But when you start calculating the sample mean and its distribution, take a look at these last two sets of graphs. What's happening to the shape as you increase the sample size, as you go from, say, 10 or 2 to 10 to 30? What's happening to the shape of this distribution here? It's becoming normal. Now, if you start out with a normal distribution, you're still going to have a normal distribution. But the bottom line is that there's two conditions under which you can have a normal distribution for your sample mean. Your sample mean itself is a random variable. If I wanted to try and find the average age of this class and I was feeling lazy and I was going to estimate it by, taking, 5 students from the right, or maybe 4 from the middle, or 3 from the left, whatever I chose, those values are random variables. But the sample mean itself has its own distribution. It has the same mean as its parent population, but its standard deviation changes. It's sigma over the square root of n. And that's kind of nice, because what it means is that when you sample more, you get more information and less uncertainty. Take a look at these 3 distributions. They're for successively large sample sizes. And if you're trying to estimate the population mean of 100, which one of these distributions do you think is going to get you closest? The first one, the second one, or the third one? Where am I most likely to get a value close to 100? From the one that's really spread out, less spread out, or very compact? Very compact. And so by dividing by the square root of n, by increasing our sample size, you're more likely to get a value, an estimate of our population parameter, which is close to mu. So what's that got to do with this next problem? Well, let's take a look at it. There's 2 parts, and you should expect 2 parts on your exam. First one's worth 4 points, second one's worth 6 points. An airliner carries 150 passengers and has doors with a height of 72 inches. Heights of men are normally distributed with a mean of 70 and a standard deviation of 3. If a male passenger is randomly selected, to find the probability that he can fit through the door without bending. Okay, so let's draw this. So here's kind of like the part A to this. And when I draw these, I'm not trying to draw them to scale in any way. I'm just trying to draw a nice basic distribution. So this is going to be X is distributed normally with a mean of 70 and a standard deviation of 3. Ryan, what should I put down here? What number? Yeah, 70, because that's the mean. It says heights of men are normally distributed with a mean of 70 and a standard deviation of 3. If a male passenger is randomly selected, find the probability that he can fit through the door without bending. Oops, there we go. Without bending. So if the door has a height of 72, where are the people that don't have to bend? Are they to the right or to the left of 72? To the left of 72. So, yeah, to the left of 72. Before you do any calculations, before we calculate this probability at all, can anyone tell me anything about this probability, what they expect? Yeah, well done. Bigger than 0.5. As a reminder, underneath your normal curves, half the area is to the left of the mean, half the area is to the right. Since this point is to the right of the mean and we're looking to the left, we expect a value that's greater than 50%. So the reason I mention this is because I want you to look at your answers and make sure that they make sense. So is that going to be norm distribution or norm inverse? Norm distribution. Good. You're going to start out with a number and try and find an area. So let's rename chapter 6. So let's take a look here. It would equal norm distribution 72 comma 70 comma, let's see, 3 comma true. Great. So, about 0.7475. So let's write that one down. So it equals norm distribution of 72 comma 70 comma 3 comma true, about 0.7475. But that's going to change when I look at the second part of this. Before I get there, are we okay with the first part? Thumbs up there? All right. Let's take a look at the second part. And again, I'm just going to draw a nice normal distribution. Something like that. Let's draw a line down here. If 75 passengers are male, find the probability that their mean height is less than 72 inches. So again, we've got a 70 and a 72 we've got to deal with. But this time we're dealing with the sample mean for samples of size 75. Its distribution is no longer the one that comes from our parent population. What is the distribution here? What should I write? Well, it's still going to have a normal distribution. Has a mean of 70, so these two are the same. What does change?
3 divided by the square root of 75.
Well done. Thanks, Matilda. 3 divided by the square root of the sample size. Our sample size is 75. Now what's going to happen is that's going to shrink the standard deviation. This should be depicted much narrower than our original graph. And there's going to be more area to the left of 72 and underneath the curve. So let's see if we can't figure that one out. So again, I want to shade all of this here. Now, if you want to, you can do one of two things. You can either just take out your calculator and get a numerical value for that, or you could let Google Sheets do that for you, and you would do that by using norm distribution of 72 I should put, 72, then 70, and 3 over the square root of 75, and I'm running out of room here, 75, comma true. So that's a way to get Google Sheets to calculate the square root of 75 for you. Basically, all you have to do is copy the previous command and just edit in for the square root of the sample size. So that's exactly what I'll do on my version of Google Sheets up here. So I'm just going to take that one and copy it and divide by square root of 75. Bam. How would you round that probability off if I asked you to round it off to the nearest 4 digits? Yeah, it's approximately 1.
Can you click on the cell?
Basically, it's a near certainty that they would have an average height less than 72 there. That's a good one. I would fully expect something like that. All right. I do want you to know, how the standard deviation plays a part in changing things when you're talking about the distribution of the sample mean. There's 2 conditions under which X bar has a normal distribution. Your sample size is greater than 30, or your original population was normally distributed. Nice. Comments or thoughts on this one? That's definitely a good one.
What was the answer to that?
It's virtually 1.
Okay, okay. Just want to make
Yeah.
sure my answer was right.
Yep. Okay. There's a couple more things to go over. Some other things I would know. Definitely the difference between R and R squared. The first one's the linear correlation coefficient that measures the strength of a linear relationship. The second one's the coefficient of determination. It tells you how good your model is. But I'm going to do that in kind of a separate video as I pass out the tests and talk to you about the tests. So I think that's it for this one.